Okay, we're continuing on chapter 8, I think. And we talked about last time. Yeah. We talked about how to calculate empirical molecular formulas, or actually empirical formulas. So remember, empirical formulas are the simplest sort of whole number ratio, what's present. And a couple of steps that we follow to calculate our empirical formulas is if we happen to be given everybody in percent composition, we want to kind of convert those into grams. And we could do so by assuming we have 100 grams of the particular compound. What that'll do is keep the percentages and the grams basically the same. Um, if it's in some other unit, basically you need to get it into grams. So whatever unit may be, and you do need to get them into grams. Once you have them in grams, you can convert grams to moles. As we talked about a number of times, again, from the periodic table, our molar mass, which are grams per mole that we get from the periodic table, are a conversion factor to do so. Once you have the moles, then you divide by the smallest number of moles. And at that point, if you divide by the smallest number of moles and you do hit all whole numbers, that would be then your empirical formula at that point. Now, if you divide by the smallest number and you do not hit all whole numbers, remember there are some numbers, for example, like 1.33, 1.5, etc. These are, again, too far to round, so we do have to sort of find to multiply those numbers by that will turn them into whole numbers. So again, for example, here we would multiply everybody by 2, and that would give us a 3 for that particular guy and so forth. So you really shouldn't round too much when you're doing empirical formula unless it's really, really close to the whole number. So make sure that, thank you. Make sure that you don't do too much of that rounding unless it's really, again, really, really close, either below it or above it. Any questions on that there? All right, so I don't think we did this one, I think. So let's do this one here. What is the empirical formula for this guy? And carbon is 12.01. Hydrogen is 1.008. And our friend oxygen there is 16. Okay, let's take a look here. We're going to go just very quickly take a peek here at the percentages. Remember, you do want to make sure that they add up to about 100%, and they do in this case. So we could assume again 100 grams. And all that's really going to do is just keep those percentages and the grams the same number. So we'll have 49.3 grams of carbon. We'll have 6.9 grams of hydrogen and 43.8 grams of oxygen. Once again, we're going to use the molar mass from the periodic table to convert these guys into moles. So we'll go 1201 per gram. We'll go with 1.008 grams per mole and 16 grams per mole. So that will get us here, 49.3 divided by 12.01. And I'll get us 4.1049 moles of carbon. We'll do the same thing for the other two, 6.9 divided by 1.008, 6.8452. And for our oxygen, 27375 of oxygen. Again, at this point, we always are going to divide by the smallest number of moles. So in this case, it does look like it's oxygen. So we're going to divide everybody here by oxygen. Obviously, that gives us 1 there. For our others here, gives us basically 1.5. And for our other guy there, gives us basically 2.5. So in this case, by dividing out, we would get an empirical formula of C 1.5, H 2.5, and then O. Obviously, as we talked about, these are not whole numbers. These are too far to round. You could probably see that actually one number will correct both of them. We could divide everybody here, not divide, but multiply everybody here by 2. And if we take 2 times this guy here, that would give us C3H5O2. And that would be our empirical formula. Any questions on that there? So again, if you don't hit that whole number, you need to find a factor in this case. And in a lot of cases, probably if you have multiples that are not whole numbers, one factor should probably clear them both in most cases. Any questions on that one? All right, then let's talk then how to calculate a molecular formula. So to calculate a molecular formula, you really need 3 pieces of information given to you. You need the empirical formula. So either it will be given to you or you'll need to calculate it like we've been doing. You also need the molar mass of the compound. This is usually given to you in the problem. So somewhere in the problem, they will say, hey, the molar mass of this compound is this number. They may also give you like a range, like, hey, it's between like 90 and 100 or something like that. If they do give you a range, you could use really any number in that range. You could use the high, the low, I could use the middle there or in between. And you will need to know the molar mass of the empirical formula. So you'll need the empirical formula and the molar mass of the empirical formula. Once you have the molar mass of your empirical formula, you will take the molar mass that was given to you. You will divide it by the empirical formula's molar mass, and this will give you a number. And this number is what you would multiply the empirical formula by to get to the molecular formula. So let's just say we had a 3 and we had this as our empirical formula, like we just maybe calculated-ish. We would then come through here and go C6H9O3 would be our molecular formula. So we'd multiply it by 3. So that is a factor which you multiply the empirical formula by basically to get the molecular formula. I would say at all the places you could be a little bit more generous in your rounding when you do this guy. So even if it's not necessary, right at a whole number, that one you can sort of round to a whole number. So you can be a little bit more generous in terms of your rounding on that one. Any questions on that there? All right, so I want to try one here. The empirical formula for acetic acid is CH2O. What is the molecular formula if the compound has a molar mass of approximately 60 grams per mole? Okay, so let's look at this. In this particular case, we are given the empirical formula. We don't have to calculate it. We are given the approximate molar mass of our compound, which is 60 grams per mole. So really in this case, we need the molar mass of our empirical formula, which would be 12.01 plus 2 times our 1.008 plus our 16 here. And that's going to give us here about 30.03. So we're going to take the approximate molar mass of our compound, which would be 60 grams per mole, and we'll divide it by 30.03. And that's going to approximately give us basically a factor of 2 in this case, basically 1.99, which is pretty close to 2. So that 2 is the factor by which we're going to multiply our empirical formula by, which means our molecular formula would be C2H4O2 in this case. Questions on that one there? All right, so let's take a look at one where you might have to calculate an empirical formula as well. All right, so nitrogen and oxygen, this one, we want the molecular formula, and it has a molar mass between 90 and 95 grams per mole. Nitrogen is 1401, oxygen still 16. Okay, so in this case, we are looking for the molecular formula. So again, there's really three things that we need. We need the empirical formula, we need the molar mass of the empirical formula, and we need the approximate molar mass of the compound. That is given to us right here. That is our range of 90 to 95 grams per mole. We're not given the empirical formula, so we do need to calculate that like we've been doing first. So we're going to start there. It's already in grams, so we're going to take our grams of nitrogen. We're going to use the molar mass from the periodic table to convert it into moles. We also have the grams there of our oxygen, which we also are going to convert into moles. And if we do all that good stuff there, 1.52 divided by 1401, that looks like a 0.108 moles of nitrogen, and a 3.47 divided by 16 looks like a 0.21, and we'll call it 7 moles of oxygen. In this case, we're going to divide by the smallest, which does look like our nitrogen here in this case. It's going to give us a 1 there. Essentially gives us a 2 there. And we did hit whole numbers basically in this case, which means our empirical formula would be NO2 is our empirical formula. Any questions on that so far? The reason we have to do that is now that we have the empirical formula, we can actually get the molar mass of the empirical formula, which is the other thing that we need here to calculate our molecular formula. So we got that guy, we got that guy. So we're shooting for this guy now. So that's going to be a 1401 plus a 2 times 16. And that's going to give us 1401 plus a 32, basically 4601. Now, in this particular case, the approximate molar mass of our compound is a range, which means, as I mentioned earlier, you can really choose anywhere in that range. So, for example, if you wanted to do the low end of the range, you would do 90 grams per mole divided by 4601. And that would get you something like 1.96. If you did sort of the middle of the range, like 92.5 over 4601, and you get about a 201. And lastly, if you did sort of the high end of the range, 95 divided by our 4601, you get about 206. So you don't have to do low, medium, or high, but this is just to show you. We essentially got, no matter where we chose in the range, right? Basically a factor of 2 is basically what we got here. So pretty much they all sort of ended up as a 2. And that is, again, what we're going to multiply our empirical formula by to get to our molecular formula, and this would be our molecular formula. I will say sometimes people will write it like this with the 2 on the bottom. Personally, I just like to distribute it, so you just get the real formula there instead of like parentheses and stuff like that. But you might occasionally see maybe a book kind of write the answer like that. Any questions on that one there? Yeah.
Is it okay that the original
It is in this case, when you have just grams like this, just given grams, it doesn't need to add up to 100. What you would want to make sure of, for example, another way you might see a problem like this is they may say something like you have a 4.99 gram sample of something. then you would want to make sure that those grams would add up to like 4.99. But without that being said, you could just assume those are the grams. You don't have to worry about it adding up. If you have a percentage, you do need to make sure that they add up to 100. Yeah. Other question? And same thing with this. If it did say something like, hey, maybe it said you have a 6 gram sample and they gave you these grams, right? So when you would add these up, you would be missing some grams, right? And it wouldn't add up to 6. That would mean that there's probably another element there as well. And you would have some type of information to let you know. It'd probably say like, it's made up of nitrogen, oxygen, and like fluorine or something like that. And that would be how you would be able to figure out the amount of fluorine. Other questions? Yeah. No, in this case, because a lot of times problems will give you an actual just one number as the molar mass, but in this case, they did give you a range, because remember, this is like based off of like experiments. So sometimes they may give you like a range, like it's somewhere in this range. So because they gave us this range of molar mass for the compound, you could choose kind of the low range, higher range, anywhere in that range, and you'll get basically the same answer. And you don't have to do all 3 of them. I just did it to show you that basically you get basically the same answer no matter what you chose. So. Yeah. No, I don't think so. Yeah, because ideally, and also as I mentioned before, this is a place where when you're doing this part of it, you can be a little more relaxed in terms of rounding, because it really should hit a whole number, because that's the relationship right between the molecular formula and the empirical formula. The empirical formula is the whole number ratio of what's present. So that ratio, when you kind of calculate for the molecular formula, that number should really be a whole number. So you could be a little bit rounding to a whole number on that place pretty easily. All right, let's try one more here. We got phosphorus and oxygen. Molar mass is 283.89 grams per mole. Phosphorus is 3097. Oxygen is 16 here. Okay, so let's take a look, see how you're doing. In this case, we're looking for both. And reminder again, for the molecular formula, we do need the empirical formula, and the empirical formula is molar mass. In this case, we are given the molar mass of the compound, which is one of the 3 things that we need. But we do need to calculate the empirical formula first. We have the percentages. So as to the earlier question, and because we do have percentages, these are where we want to make sure that it does add up to about 100, and it does. That means that we can assume 100 grams here. That will turn us into 43.64 grams of phosphorus, which we could convert into moles by using our molar mass. We also would then have 56.36 grams of oxygen, also using the molar mass there from the periodic table. We'll convert that. That's going to get us here 43.64 divided by 30.97. That's going to give us about a 1.409 moles of phosphorus. For our oxygen here, will get us 3.5225 moles of oxygen. In this case, it does look like phosphorus is our smaller number, so we're going to divide everybody by the moles of phosphorus. That obviously gives us 1 for our phosphorus, and for our oxygen there, going to get us a 2.5. So at this point, our empirical formula would be PO 2.5. Once again, we cannot have that sort of decimal there. So again, if you take 2.5 and times it by 2, that's going to give you 5. So that is the factor by which we want to multiply everybody by. And that would give us an empirical formula P2O5. Any questions up to that point there? Now that we have the empirical formula, we then need to get the molar mass of it so we could get our molecular formula. So the molar mass of this guy here going to be 2 times our 3097 plus our 5 times 16. Going to get us there. It's like 141.94, 141.9 grams per mole. So now that we have our empirical formula molar mass, the molar mass of the compound, we're going to take those two basically and divide them. So we're going to take 283.89. we're going to divide it by 141.9. And that's going to give us a factor to multiply our empirical formula by to get to our molecular formula. And we basically get about 2. And that means we're going to multiply that by 2, gives us P4O10 as our molecular formula. Any questions on any of those steps there? Okay, so if you do have, by the way, a problem like this, and you do have the percent composition given to you, you do have the approximate molar mass of the compound given to you, you could actually work this problem slightly different if you like. If you know those percent compositions and the molar mass of the compound, and you can use the percent composition to your advantage here. So let me just show you an alternative way that you could solve this. So I'm just gonna kind of clear what I got on here. I think just borrow this page. This has the numbers. So what we know is when we look at a percent composition of this, that it is about 43% phosphorus and 56% or so oxygen. That is the molar mass of the compound, which means we could take our percentages and convert them into a decimal, divide by 100, which gives us 0.4364. And if we times it by our molar mass here, that will basically give us how many grams of phosphorus there is. And we could do the same thing with the percentage for oxygen. We'll take our 0.5636, which is again divided into the percentage by 100, times it by our mass of our compound here. And we will end up with about 160 of that 283 is our grams of oxygen in this case. Now that we have the grams of each of these guys that make up the molecular formula, we could divide each by the molar mass, 30.97 grams per mole, and 16 grams per mole. And if I do that there, 123.8895 divided by 30.97, that looks like a 4. I'm going to take a 160 divided by 16. That looks like a 10. And that would give me my molecular formula. Just go with an O there. That would give me my molecular formula right off the bat. And once I have the molecular formula, I know the empirical formula is the simplest ratio, which means I can reduce this down by 2, right? Which would get me basically divide by 2. P2O5 is the simplest way I could bring that back down, and that would get you to your empirical formula. So if you do have the percent composition given to you and the molar mass of the compound, and you want to work from the molecular formula backwards, you can, and just reduce down the molecular formula. So again, you could really only kind of do that if you have those percent compositions given to you. If you don't have them, it's just easier to go the other way and do it like we've been doing. But this is another way that you can do it. Yeah. In terms of, I'm not sure I understand your question.
Like the exam specify use this or use that, or will be up to us?
It will ask you to solve for one of those if that's what you're asking. Yeah. Yeah. But this method takes you this way, it takes you from the molecular formula back to the empirical formula. But once again, if you don't have those percentages, it's just easier to go the other way and kind of do that. All right, any questions on how to calculate molecular formula, empirical formula, any of those things? All right, so that should wrap up chapter 8, I believe. So we're going to go now back, I think, to chapter 10. So just give me a second here. 6, so we're going to talk about chemical equations, how to balance equations. And then we'll go off to, I'm not sure yet. I'll flip a coin. We'll see which way we'll go. All right, so it's a pretty short chapter. It's just about really chemical equations, chemical reactions. Remember that a chemical reaction is a chemical change, right? And that means that what you end with are fundamentally different things. Ways that we can see that maybe a chemical reaction has occurred, maybe a color change, a solid that's formed. Maybe you start to see bubbles. Usually, again, if you see bubbles that are forming, that's usually an indication that you made some type of gas that wasn't there before. Those are usually what those bubbles represent. Heat or flame is produced, or heat is absorbed. Clearly, I think a flame would be visual. But again, if you're filling a test tube or holding onto a test tube and it starts to feel warm to you, that again would imply that there's energy being given off as a result of that reaction. That's because your hand's absorbing all that energy. This is why it feels hot to you if you're holding it. And vice versa, if you're holding a test tube and it starts to feel cold to you, that would be more of an endothermic process or reaction because it's absorbing energy. And again, it's taking all the heat and energy from your hand, which is why it feels cold to you when you're doing that. So lots of visual sort of changes that you can see indicate some type of reaction has occurred. For example, if you throw a piece of metal in there and the metal kind of goes away, usually that means the metal changed into some other things. And it's not going to be a physical change like you dissolve salt or anything in water. That would be a chemical change because there's no way to get that metal back again in there. So here's an example, right? All those bubbles are hydrogen gas and oxygen gas being formed through electrolysis of water, which you'll do in an experiment, not like exactly like that, but you won't drop the battery right in there. But you'll do something like that. Again, here are some of the signs and clues that a reaction took place. Again, we see some color changing, which could indicate the formation of a new species that has that color. Obviously, we'll do this one actually. We're pouring this together. You'll make this yellow solid or precipitate. And again, a solid that wasn't there before definitely means that something took place. As we'll talk about when we talk about reactions sort of happening, there's really three reasons why a reaction occurs. Here's obviously some bubbles. And as we'll talk about in that later chapter, there's three reasons really why a reaction will occur. It is basically a transfer of electrons happening. It is a formation of a solid. And it is a lot of times the formation of water. As we'll talk about when we talk about different types of reactions, which is in chapter 7, you pretty much could boil down every single chemical reaction to one of those three things occurring. Either there's some electrons being transferred, there's some type of solid being made, or you make water. Pretty much they all boil down to one of those three things sort of happening in that particular case. And obviously that's a flame from your Bunsen burner. Bless you. There's the metal reacting, creating again gas bubbles as we see here as a result of that. So let's talk a little bit about the chemical equation. Chemical reactions are represented by chemical equations. Chemical equations basically use the symbols for everybody involved. And a chemical change always involves the rearrangement in the way atoms are grouped. When we have a chemical reaction, it's all about electrons. And it's all about electrons and bonds. So pretty much we break all the bonds on the reactant side and we make all the bonds on this side of the arrow. And that is really the only thing that's happening in a chemical reaction is breaking bonds, making bonds. That all involves only electrons. And as we know from our previous chapters, the one thing that's most important in terms of the elements are protons. So nothing in the nucleus is involved in a chemical reaction, which is why if we start with 4 carbons on the left-hand side of the arrow, we should end with 4 carbons on the right-hand side of the arrow. They may just be in different things, but we don't lose or create elements along the way. So for example, here, if we take hydrogen gas plus some oxygen gas here to form water, this is what is referred to as an unbalanced equation. Also a very good reminder that sometimes you're given things in words. You want to make sure that you do get the correct formulas down before you do anything in terms of like balancing the equation. That's also a good reminder that if you have something that is one of those diatomic elements, diatomic molecules, you need to make sure that you write them as diatomic molecules. Otherwise, your equation will not balance probably correctly. So if you have anything like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, or iodide by itself, make sure that they come as 2s. Now, when we look at this equation, we could read this a couple ways. It is sometimes referred to when you talk about hydrogen, oxygen, or even nitrogen. They sometimes refer to as like molecular hydrogen, molecular oxygen. And when you see that in words, that means basically, again, H2O2 and so forth. We could say molecular hydrogen reacts with molecular oxygen to yield, which is pretty much what the arrow represents, to yield, our water in this particular case. Or if it said hydrogen gas and reacts with oxygen gas to form water, that would be another way that you can see that. Now, when we look at this equation, what's wrong with the equation is what I was just talking about. We don't create nor lose any elements along the way. So this is an unbalanced equation, basically, right? And you can make like a table here, kind of the reactant side and product side. You can look at your elements here. And on the left-hand side, we have 2 hydrogens. Over here, we have 2 hydrogens. Again, the number goes to the guy to the left. Over here, we have 2 oxygens. And over here, nothing written means 1. And we have 1 oxygen in this case. So we do not have the same number of elements on each side of the arrow, which we need to have in order to have a properly balanced equation. And that again is because we do not lose or create things, our elements along the way in this chemical reaction. So the way that we fix that is we fix it really by only when we balance equations. We fix it by putting coefficients, which are our numbers that come in front, is the only way that we fix things. So for example, here we would need maybe a 2. Which if I did that would then give me 4 hydrogens on the right. And this 2 goes to everybody behind it. And that would also give me 2 oxygens on the right-hand side. That is pretty much what happens in most cases when you go to balance the equation. You fix one thing and kind of screw up something else. So in this case, although we just fixed the oxygen, we now unbalance the hydrogen, which means we would then need to go to the other side and also put a 2 there. And that would give me, once again, 2 times 2 is 4. And we would still have our 2 for the oxygen in this case. So it's really important when we balance equations or whenever you use an equation that it is balanced. And again, the only way that we really do it is by changing those coefficients. You never change any of the little numbers, subscripts, or anything like that. We never change those guys. If I change the little guys on the bottom, I am essentially changing what it is, right? So it would no longer be like water or something like that. So we never do that. We never insert big numbers between letters and stuff, the crazy things people do. So there's always those numbers in front. So here again, we can fix it by balancing, as I mentioned, using our coefficient. And we will eventually have a balanced chemical equation, which is pretty much always what you want to make sure that you have when you're doing anything with an equation. I would say that if you see an equation that does not have numbers in front of it, or coefficients, I would take a really hard look at it to make sure that it is balanced. And if it's not, make sure that you do balance it. I would probably say 99.9 times out of 100 that if you do see coefficients in the equation, it's probably balanced unless somebody's trying to trick you or something like that. It's going to probably be balanced. But you should still take a second just to make sure that it is properly balanced. So there's a lot of calculations that we're going to talk about, especially say in chapter 9, that uses the equation. And if that thing is not balanced, then you're in trouble along the way. So let's talk about some of the parts of our equation, even though we kind of touched upon it, I think, in earlier chapters, which were later chapters, I suppose. On the left-hand side of the arrow are our reactants, and our reactants are our starting material. So those are our reactants right there. And our product, the stuff that are formed over here on the right-hand side of the arrow, reaction always goes from reactants to products. And again, We want to make sure we have the proper coefficient there for everything to be balanced. This is something that we'll see in a later chapter, ways that we can interpret a chemical reaction. We could use those coefficients as the number of, for example, in this case, molecules of each of these. This relationship here is one that we will use a lot in chapter 9, which is known as the stoichiometry relationship, or mole to mole relationship. We can also use the coefficients to say for every 2 moles of H2, it reacts with 1 mole of O2 to give you 2 moles of H2O. This is our law of conservation because we have basically 4 hydrogens on the left and 2 oxygens. Those add up to about 36 grams of reactants. And since we should still have the same number of elements on those side, it will also add up to 36. That's because the hydrogen on the left is about 1.008 grams, and the hydrogen on the right is also 1.008 grams. So they're the same mass on both sides of the arrow. Other information that you commonly can see in equations are the states of matter. So G for gas, S for solid, and L for liquid. So these again are the states of matter, which you sometimes will see. We'll also see, I think, in the next slide, but aqueous is also something which means it's a water environment or a solution that you also see written to the right of formulas here. So we know these guys are in gas states, liquid, gas, solid happening there. Although a lot of times we do look at chemical equations for chemical reactions, which are chemical changes, we could also write chemical equations to represent physical processes that are happening here. And that's what we see here. That is liquid water going to solid water, which is basically freezing water. That is a physical change, and we can use an equation to represent that. That is liquid water going to gas, which is steam. That's evaporating liquid water. Also a physical process. So we can use equations to represent physical processes, although in a lot of cases it is used to represent chemical changes that are occurring. We also can sometimes see things written on top of the arrow. For example, water written up on the arrow means that a lot of times you're dissolving this in water, and that gives us our aqueous. A reminder that there is a difference between the L symbol and the aqueous symbol. An L is typically a pure liquid by itself, like if you had just pure water. Something that is aqueous is basically a solution. So if you took something like water and you took, like we have on the bottom there, some sodium chloride that's solid, they will dissolve and make a sodium chloride solution as the salt will dissolve in the water. So something that's aqueous is really a solution. It's really a mixture of 2 things together. They're both in the liquid state, but something with an L is kind of a pure substance by itself. There's nothing else involved with it. Other things that you sometimes will see on top of the arrow, catalyst. And a catalyst is not a reactant. It's not a product, and it does not get used up in the reaction. Typically, a catalyst is there to speed up the reaction. There are catalysts that actually slow down a reaction, but in most cases, people think of it as speeding up a reaction. And this can be things like metals. So sometimes you'll see metals written up there, like platinum. This could be things like acids. So maybe you'll see like H+, which represents an acid that's up there. So a lot of times up on top of that arrow, you'll see those catalysts. They, again, typically will speed up the reaction, but they're not considered a reactant nor a product in a particular chemical reaction. All right, so let's talk about balancing equation and ways to balance equations. And then we'll just talk about doing that, I suppose. But a couple of really important things to keep in mind is what I said earlier. Sometimes you may be given things in words, and you want to make sure that regardless of the balancing aspect of the equation, you want to make sure that you always just start with the correct words first. And like we did with nomenclature and just putting things together correctly, you want to start with the right formulas. and then you want to balance. So that's a really important order that sometimes people screw up on. You want to get the formula first and then balance. So that is the order at which you should do it. People oftentimes screw this up when they are given like the reactants, which is possible that you will be given just the reactants and you need to predict what happens on the product side. So a lot of times people try to balance and write formulas at the same time, and they end up with the incorrect formula and things never balanced correctly and stuff like that. So always keep in your head that you should get just the proper formulas down first, regardless of the balancing part. Once you have all the proper formulas, then you should go back and change the coefficients to get it balanced. Once you have that, that would be your unbalanced equation. You could start with the most complicated molecule if there is a really complicated one. You want to use coefficients until really everything balances out on both sides. Really, the two things that you need to make sure of when you're all said and done is once you are balanced, all the coefficients need to be whole numbers. And they need to be the simplest set of whole numbers. So what do I mean by that? I mean, so let's just say, for example, you balance this equation, 2a plus 4b goes to 6c. Let's just say this equation is balanced. But what we could do with all these coefficients is we could actually reduce them all down by 2. And the properly balanced equation would be something that looks like this. And that is what you should do. So sometimes this occurs because some people could maybe see bigger numbers to balance in the equation. But if you could reduce down all the coefficients by a common number and still hit all whole numbers, then that is the way to properly balance the equation. Any questions on that there? As I mentioned before a second ago, only coefficients. We never change any of the smaller numbers or anything like that. Here's another approach in case you like this approach better. But I would say probably most people go with a trial and error, kind of throw some numbers on one side, then the next, and kind of get it to balance at that point. So let's just see how we go about doing this. And here's a few more of those steps. Whew, there you go. All right. So let's take a look at this one here together. Now, if I was going to balance this equation, I think it's usually helpful as well to make a little table. It just kind of organizes things. It gives you an idea as to, what you have going on. So I'm just going to rewrite this here. Have a little bit more room to put numbers in front of it. All right, so if I'm going to make a table here on the reactant side, product side, I'm just going to list my elements. I got nitrogen, oxygen, and hydrogen. Here I'm going to count up what I got going on the left. I got 1 nitrogen, which is here. I have on the right here 2 nitrogens. On the left, I have 1 oxygen. On the right-hand side, I got 1 oxygen right there. Left-hand side, again, that 2 means I have 2 of those. And for hydrogen, same deal, I have 2 of those. So by making this table, I could clearly see in this case, everything is balanced except for the nitrogen, which means that's probably a good place to start. So we're going to fix the nitrogen here on the left. Remember that we can only change the coefficients. So I'm going to put a 2 in front of my nitrogen on the left. When you put that coefficient, it does count for everybody behind it. So everybody gets the benefit of that 2. So that's going to give me 2 nitrogens. That will also give me 2 oxygens. And I didn't do anything with the hydrogen, so it will still be 2 in this case. As I mentioned earlier, this is very common in what happens. You fix one thing and kind of screw up something else. So that's not a big deal. We can see from our table that oxygen is probably the good place to go to next. And we're going to fix the oxygen by also putting a coefficient in front, which is a 2. Once again, this guy does go for everybody behind it as well. So that's going to give me 2 nitrogens. That will give me 2 oxygens. And now I have 4 hydrogens in this case. Again, the table here shows me that probably hydrogen is where I should go next, since that's the only thing not balanced. And we could fix that by simply putting a 2 right there, which obviously goes to the guy behind it, giving us 4, 2, and 2. And now we have a balanced equation. So making these tables are kind of helpful. It just sort of organizes things for you. It also gives you an idea maybe where to start, where to go next, and it's sort of helpful to do rather than just kind of randomly throwing numbers up there at it. You know, sort of organizes a little bit. Any questions on that one? All right, so let's try the next one then and see what you come up with here. Balance this equation and see what you come up. Okay, let's take a look. So again, I'm gonna make my table here, reactant side, product side, got a little carbon, hydrogen, and oxygen. So we got 3 carbons there on the left and 1 on the right. We have 8 hydrogens there on the left and 2 here on the right, and 2 oxygens there on the left. Oxygens on the right-hand side, we have 2 there, and we don't want to forget about that guy over there, right? So that is 3 oxygens here on the right-hand side. In this particular case, nothing's balanced. So I personally would pick something that seems really easy to balance, and to me, seems like carbon would be a pretty easy guy to balance. So I'm going to balance my carbon by putting, again, a coefficient here on the front. That, again, does distribute to everybody behind it, and that would give me 3 carbons, still 2 hydrogens. Now I have 6 oxygens there, plus 1 more there. It's going to give me 7 in this case. The next easiest thing to balance is actually hydrogen. The reason I'm not going to go with oxygen first is oxygen's in a couple of things on the right, 1 thing on the left, so it's in a lot of places. So hydrogen, though, is only in 1 place on each side, so that seems like the much easier approach to go with. So to do that, we will put a 4 in front of the hydrogen on the right. Once again, that 4 does go to everybody behind it, and that's going to give me 3 carbons. Hydrogen will be 4 times 2, which is 8. Now, in terms of my oxygens, I got 3 times 2, which is 6 there, and I also have 4 there, which means I got a grand total of 10 oxygens happening at this point. Now I could clearly see oxygen much easier to balance at this point. We just need to put a 5 right there, and that would give me 3, 8, and 5 times 2 is 10 in this case. Yeah. Any questions on that there? Let's try a couple more here then. All right, balance this guy here. Diboron trioxide reacts with water to make boric. So see what you come up. Good look. So you have this in words. I know you have the equation given to you, but again, if it wasn't given to you, you want to start with just the proper formula. So diboron means I have 2 of them, and tri is 3 of those. And it reacts with water, which is H2O, and forms our boric acid, which was given to us here. So here I was not concerned about any type of balancing. I just want to make sure I got the proper formulas down first. Now that I do, now I could go to my table here and do my balancing, which is our boron, oxygen, and hydrogen in this case. On the left-hand side, we have 2. Right-hand side, we have 1. Left-hand side, I got 3 oxygens there, plus 1 more there, makes 4. Right-hand side, this 3 does get distributed to everybody inside the parentheses here. So we will have 3 oxygens. Left-hand side, 2 hydrogens, and also, once again, R3 is going to get distributed in as well. Not a lot to work with here, so I'm thinking we're just going to go with our boron. And to balance that, I'm going to go with a 2 in front. Now, this 2 does go to the guy behind, and it does go to everybody in the parentheses as well. So you do have to do a little bit of distributing there. That would get us 2 borons. We had 3 oxygens times 2 is 6, and 6 for our hydrogens. So again, on that case, 3 comes in to gives us 3 hydrogens, the 2 in front, then gives us our 6 hydrogens at that point. So you got to, again, take account of both of those things. At that point, not much to work with on the right-hand side. So let us go with perhaps the hydrogen might be the easier move. Again, oxygen's in a few places. So I'm going to balance the hydrogen. And on the right-hand side, I have 6. The left-hand side, I have 2. So to balance it here, we're going to go with 3. That's going to give me 2 borons. That will also go to everybody behind, which means I have 3 oxygens there and 3 more there, which gives me 6. And 3 times 2 gives me 6, and actually that takes care of everybody, which oftentimes happens when you're balancing. Sometimes everything should just kind of fall into place. Any questions on that one there? All right, I think we'll lay it up there for